All right, go ahead, 5.30. Guys, tell me what it says.
Your piece of L is one.
PL.
PL is 110 kilowatt.
All right, the power to load is 1 kW. Right, go ahead.
110.
Oh, 110. Uh-huh. Voltage is what?
480.
All right. And that's RMS too, by the way. Go ahead.
R is 0.15 ohm.
This is the line, the line resistance 0.15, did you say? 1.15?
0.15.
Okay, thank you. Go ahead.
Power factor is 0.88 line.
Go ahead.
The one is about complex power.
All right, they want S, sure. They want S complex for the whole circuit. They want anything else? Voltage at the source? All right, let me draw this for you. What it's saying is there's some source voltage that's at the power company's end. And this source voltage has a line in front of it before it feeds the load. And the line has a resistance of 0.15 ohms. Now that line impedance could be reactive, yes sir?
This problem is looking for the S on both sides.
That's fine.
Yeah.
Well, I mean, we can get the complex power associated with the source and the load, all right, so it won't be a problem. But go ahead, and there's nobody else. Okay. Then here's the load. This is the load right here, ZL, and it's dissipating 110 kW. It has a power factor of 0.88, and it's a lagging power factor. And this voltage is given as 480, which is common. At 0 degrees, it's RMS. And so they want to know complex power, they want to know voltage at the source, and things of that nature. First thing we need is a line current. That's the key to all of this. We want the line current right there. And the way we get it is, we remember the equation that power, average power, right, is equal to, that's what this is, P load. That's equal to VRMS times IRMS times the power factor. I'm just going to abbreviate as PF. I know it's the cosine of theta V minus theta I. I know that, but it's just abbreviate PF. Is everybody all right with that? So now we can calculate the magnitude of I directly. I can say that IRMS, which is I line, they're the same things, is equal to P, which is 110 times 10 to the third, divided by 480, right? That's the line voltage, divided by the power factor, 0.88. And what do you get for this magnitude of I? This is only going to be the magnitude, like I said before. Anybody?
260.417.
260.417. How many got that? With me? It's a straight division thing here. It's nothing tricky. I have that. Next thing I'm going to do is get the angle associated with that, right? Lagging means the angle is negative. Got it, everyone? So to get the angle, I say that the cosine of the angle, right, of the power factor is equal to 0.88, and therefore the angle associated with the power factor is the inverse cosine of 0.88. What is it? 28.35 degrees. All right, so now I have the angle. I have current and I have angle of the current. So I can say I line is equal to 260.417 at an angle of minus 28.375 degrees. Now I've got everything I need for the rest. Yes?
So
So when you get that angle, that's theta V minus theta I, right?
But theta V is 0, so I don't even need to put it in.
Sure. So when theta V is greater than theta I, it's leading, and vice versa.
When the voltage is ahead of the current, yes. In other words, if it says leading, then the current would have an angle of positive, whatever that was, 28 degrees.
Okay, I got some wires crossed and I had, appreciate it.
Remember, everything we deal with is the current's relative phase with respect to the voltage. Now, the voltage invariably is almost always at the load voltage at 0 degrees. So that's just the way it is. If it's lagging, the current is behind that angle, right? And if it's leading, the current would have a positive angle, I should say. It's at a negative angle with respect to that. And remember, phase is something that if you think about it, when I say something's leading or lagging, what do you think of? Well, if you plotted on an oscilloscope 2 waveforms, right? If there was no phase difference, they would be identical except for the magnitude, right? If we're talking about something that's going to be, let me just show you. For the record, thank you again, by the way. If we're talking about 2 waveforms and we have one like this and another one like this, that's a sine wave, correct? And I don't want to put any more detail than I need to. All right, now what happens if I say this one is leading? Think about that. Well, it means if this is the sine of theta right here versus theta. If I add something to this, say add 30 degrees, what actually happens? I take this whole waveform and I shift it, don't I? It would do this. Let's see here. It would shift roughly like that. Anyway, you can figure it out. It shifts it. It's with respect to where the waveform is. Do you follow me? That's all I'm talking about when I talk about a phase difference. It's a shift in the relative 0 crossings, if you think about that. That's it. All right, so that's that problem. Now, I mean, that's how we get the current. Now, if we want, first we get the load voltage, VS, or the source voltage. For VS here, the way I do it is I always start at the negative terminal and I go around the loop till I get back to the positive terminal. And I just add the voltages. That's the easy one. I get an increase of 480 at 0 degrees. These have to be added with polar numbers. These are polar numbers. Plus, then I get the voltage here, right? The voltage there would be line current times resistance. Do you all agree with me, class? So now it's going to be 0.15 times the line current, which is 260.417. At an angle of minus 28.375. And you can give me VS. Somebody can. That's just, you're adding polar numbers. They're not scalars. You gotta add magnitude and angle together. You can break them up into rectangular and add just the magnitudes and then the J component of the rectangular, but you have to do it correctly. What do you get for this, anyone? Say again?
14.71. At angle negative 2.07.
Is that right?
Yeah. That's all.
Now, if we want complex power, I can tell you we can do it a couple ways. I want to first make sure everybody understands complex power. S is equal to V times I conjugated, right? That's what it is. Right? So when I look at complex power, I drew the power triangle. I drew it up last time a couple times. I come over here. And this is going to be the load right here. We always put the real power in the horizontal axis, and the real power out here was 110 kW. I know that I have an angle here of, was it 28 point something degrees? I forgot exactly. 28 what? 35 degrees. And remember, because it's I conjugated, it puts us in the first quadrant when it's lagging. Everybody remember that? So I'm here, and that's equal to the P, and then I have this portion right here, which would be JQ. And that value of Q right here would be equal to this value of P times the tangent. Please listen to me, the tangent, so it's the power right here times the tangent of this angle right here. And I'm just gonna call it theta. You all agree with me? Opposite over adjacent is the tangent of that angle, correct? So I can get Q by simply taking the power right here and multiplying by the tangent at 28.35 degrees. Not the cosine, the tangent. Do y'all follow me, class? How many do right here? I'm showing you this several different ways so you're clear about it. So that's JQ. What do you get for Q here, by the way? Guys? Take 110 kW, or 110 times 10 to the third, times the tangent of 28.35. I can't do that one in my head. Anybody? Yeah? Anybody?
59.37.
So it's J 59 point, say again? 37, and that would be K var. That's volt amp reactive. The R indicates that that power is reactive power. It's not absorbed or dissipated. It's power that goes into the unit, then comes out of the unit, if you think of it that way. Energy into, out of, into, out of. It's just swooshing around. Everybody with me? Now, that means S right here can be given as just the actual VRMS. So that would be 480, right? It's just 480, it's plus J nothing. Do you agree? Thank you. Everybody? That's times I conjugate, correct? And I conjugate would be what? Where's my, did I erase the magnitude of I too? What was I? We just calculated.
I is, that's
60?
Yeah, 260.
One something, right?
4.2.
4.2. And the angle is what? 28 degrees, right? Conjugated, it would be, or minus 28, conjugated is plus 28, right? 28 point, what was the degrees exactly?
375.
So that would be S, that's one way to do it, V times I conjugate, right? It's also equal to, you're gonna see this is S right here on the diagonal. S also is just equal to this P, which is 110 kW, plus J, that P, which is 59.37 kVAR. The K is just 10 to the third. VAR is volt amp reactive. It's indicating that this is reactive, this is real. Watts are dissipated. You never get this power back. We get this power back, you could say. And the complex power here, that S is the sum of the two, and its units are kVA. There's no R's, just volt amp. All right? That's all it is. So we could, what I'm really getting at is we could get this value doing it this way, right? Or we could do it this way. They are one and the same. Does everybody follow me, class? Now we need to know how to do it this way where we get JQ. Because what we're going to see is by adding an element today, we can actually, a capacitor in parallel, we can reduce that thing down to zero. And that's what's done a lot in the real world, and I'll get to that in a second. But getting back to this problem, now if I want the total complex power of supplied by the source, I want you to, this is going to be supplied by the source. Well, you got the complex power supplied by the load, correct, class? The complex power supplied, or I should say dissipated, sorry, the complex power dissipated by, or at the load, let me just leave it at that, at the load is over there, right? It's 110 kW plus J 59.37 kVAR, correct, class? If you just take that and do a conversion to the polar coordinates, you're going to get the one above, right? Whatever that is, okay? And matter of fact, so it doesn't matter which form it takes. But this is a resistor. One thing about a resistor, it only dissipates real power. There is no imaginary, right? So I know the power is just going to be on the horizontal axis if you think about it, correct, class? How much power is dissipated by this resistor? What would it be? It would be R times IRMS squared. You all agree with that? So that would be 0.15 times 260.42 squared. Now you can give that to me, but it's got no angle associated with it. I don't know what that is. Anyone?
10.17 kilowatts.
All right, so we've got 10.17 kW here. Now that means that the total power, complex power in that circuit, right, if we use that terminology, this, and I'll call it S complex, would be equal to the actual complex power of the load plus the complex power of the resistor R. Or it would be, if you just look, if we do this, not in polar, but we do it in rectangular coordinates, I'm going to take 110 and add 10.17 to it. So it's going to be 120.17 kW plus J, and it's going to be 59, still just J's 59.37.
Would your S bar now be able to those two squared?
Follow me on this? I just added the real power to the real power, if it's rectangular. Yes?
Is that supposed to say like S bar sub S for the source load?
This is load, S, I'm just saying this is the complex power of the circuit, S is, this is load, L-O,
Because base plus
A-D,
height.
it means at the
For a
load.
right triangle, isn't it?
And it's plus
This
S
square
of the
base square
resistor
plus
is
height squared.
dissipated, just that R, the
That's
1.15.
Pythagorean
So
theorem.
so what's S for on the left side of the equation? Is that S sub C or S sub L? On the
This?
left side. No, on the far left of the equation.
Just SC, S complex, all right? I can just leave it like this. That's the total one. It doesn't matter what the subscript is. Yeah.
The voltage on the far left, that is the RMS of the source, right?
That's the source voltage right here.
And that's RMS, or is that?
Yep, that's, all the voltages are RMS. Unless there's some, unforeseen reason not to use that. And this is all steady state. It means it's a constant frequency sinusoidal variation. There's no transients here. Now, is that what the answers are? I don't know how they have the answers. Is that it? You asked me a question. Is this, do you have the answers here, guys?
Yeah, it's
Is that it?
130. Yeah, they turn into 134 angle 26.29.
Well,
But yeah,
if you
that's
want to do it
added
that
up.
way, you can convert that to polar.
Yeah, that's correct.
It's
Added up.
fine. Either way, do you all follow me? And you can always get it by taking V times I conjugate. And those are two polar numbers, so you can always get it that way. Did you have a question? Okay. All right, anybody else?
20?
Yes.
Just sorry, there's one other question about that. Is that equation saying that the J portion of the power goes to the resistor, or no?
J,
Is this
the imaginary part is only associated with a element that doesn't dissipate power. When you have a J57K or something like that, or K bar, that's never dissipated. Watts are dissipated. Like resistors dissipate power. The units of the power are always watts or kilowatts associated with the resistor. Anytime you say see a plus J something kVR, that is never dissipated. That's associated with either the power, complex power, really reactive power in an inductor or in a capacitor. Got it, everyone? All right. Did somebody else have a question? If you look at the problems I gave you, this was the way they did it. They always got the current first, didn't they? I think they did. You need the current, and you got to get the right angle with the current. After that, the problems fall apart, usually. Correct? How many understand this? Right? I gave you the solutions, I gave you a bunch of problems, and they're all basically cookie cutter problems. Same type. There's not a lot of variation. You're just juggling numbers, aren't you, class? Remember that complex power is always V times I conjugate, and it's RMS stuff. Now today what I'm going to cover, if there are no more questions, it's going to be power factor correction. This is important.
I have one last question that's pretty minor. Is there a reason that you're notating that or A plus J, B plus H, diagram?
You can do it either way. I did it that way for one reason. I knew I just had a resistor out there, so I'm only gonna be adding to the real part. Alright, so I'm just gonna, I've got a real part, I can add two numbers together in my head usually.
Okay.
Now, but you don't have to. Now, I want to tell you this over and over again. This is our motivation. We don't, I repeat, we do not want any kind of reactive power in the circuit if we can help it. We'd like to take it and zero it out. So what we're going to do is add an element that will add, quote, negative reactive power. Most of the time, almost every industrial load that I can imagine, there's probably one I can't imagine, it always has a reactive component that's positive. The impedance would be like an inductance, right? An inductance always has a lagging power factor. It's just the way it does. It will always, if you put an inductor resistor in series or in parallel, the net amount of power will always be lagging. The current will lag behind the voltage. Follow me on this, class? Now, in the real world, almost always we have machinery that are large, really electrical machinery. They're going to be they're going to be all sorts of electrical motors that draw huge amounts of currents. Those things are basically coils and coils of wire with lots of currents turning, with large magnetic fields. It's an inductor, basically. Just trust me on this one. Which means you get most industrial supplies, or places, any mill, anything like that. The fact is that all that stuff is going to have a net effect on the power, or the power supplied to that will be very reactive overall. That's my point. Now, how do you correct that and get rid of the reactive power? Because one thing you should appreciate is reactive power means that you've got to send more. The stuff that's dissipated is only the stuff that's real power, right? So if we could get rid of reactive power, we can lower the current in the line that supplies that, number one, and lower our total amount of source voltage and everything. The power company benefits and you benefit if you can do it. And here's how it's done. Let me start by just showing you the example. I'm going to start right from the power triangle, all right? This is going to be at my load. You can forget everything else but the load itself for now. I'm going to have some P load here, and I'm going to have some JQ here. So this means this is a lagging system. It's a lagging power supply. This is the angle, and I'm going to call it theta 1 here. That's the angle, it's the inverse cosine of the power factor. Are you with me, everyone, on this? Give me a show of hands if you are, so I gotta see. All right, now if I have that, that's lagging. What I want to do is add something to this that would be a complex power, only it would be minus JQ. Does that make sense to me, everybody? So here's where I slow down and make sure everybody sees this. If I have a capacitor, and I have a voltage here, I'm just going to call this voltage V, call it just V at 0 degrees, and assume this is RMS. Well, that's going to give a current here, I. And if you remember the reactance of this capacitor, the actual reactance of this capacitor is 1 over J omega C. How many remember that? The capacitive reactance is 1 over J omega C. That's in ohms. The inductive reactance of an inductor is J omega L, right? These are things that are common. You've had many, many times probably in physics, and you've had it here. It's common. So if that's the reactance, or you can call it the impedance, I can say that I itself would be V, which is at 0 degrees, so I'm not even going to put it, divided by 1 over J omega C. Or really, the current is equal to J omega C here, right, times V. Everybody agree with that? Right, I just found the current for a given voltage, agreed? Now complex power, this is important. This is the voltage, that's the direction of current. When I talk about complex power, and I have anything at all, doesn't matter if it's a generator or if it's a supply thing, something supplying power, if there's a plus to minus voltage V across here, and put RMS, and there's a current entering the positive terminal, then the complex power associated with this the S associated with it is equal to VRMS times IRMS conjugated. Now, if that turns out to be negative, it means power is being supplied. That's what it means. If there's a negative sense to that, okay? That's all it means. If it's dissipating power, it'll be positive. I mean, it'll be at an angle too, generally. So if I look over here, now when I take a look at the power associated with this, well, that power, complex power, would be associated with that capacitor would be V, or just V at 0 degrees, times I conjugate. Well, what happens when I conjugate that, class? All right, let me ask you this. If I have 1 plus J1, call it A, what is A conjugated? 1 minus J1. So wouldn't this be just minus J? Because there's 0 in front of it, right? Sure, so it'd be this times minus J omega C times V. And you can see that's minus J omega C times V squared. And that's VRMS too. Make sure you understand that. So the complex power associated with that capacitor is really going to be equal to minus JQ, isn't it, class? And you could put it JQ sub C, indicating it's a capacitor. Everybody follow me? How many see this right here? Y'all see it? All right. You don't? You don't? You understand how I got that? Do you all understand this? All right, what happens when I conjugate it? The J becomes minus J. You all understand that? All right, what is complex power? V, this is the voltage across it, but V, times I conjugated, or times minus J omega C times V, or this right here. Do y'all see it? So it's going to be minus J times omega C VRMS squared. You follow me in this class? That's minus J, right? So if I take a net load, I'm going to do problems so you can see it, a net load like this, that has a plus to minus VRMS at 0 degrees across it. And I have a Z load here. And it has a certain power factor. Then if I put a capacitor in parallel with it, that capacitance, if this has got a lagging current, which means the power factor is going to be in the first quadrant, right? I mean, the S is in the first quadrant, follow me? Then if I add that capacitor in parallel with it, well, the capacitor's complex power is minus J omega times C times VRMS squared. So this will reduce the total complex power. How many understand the principle? Right? Now we get into the specifics. I'm going to go through a problem and show you the technical details so you can understand all of this. And this is common, by the way. You're going to see after a couple problems, it's very apparent, very easy. So check, and I like using Earl books for these things because he does a lot of problems like this. So for this problem, let me go ahead and erase that. Matter of fact, I'll tell you that what I'm about to show you is a typical kind of problem. So I'm going to have an industrial load here, all right, and I'm going to have a line voltage here of 480 at an angle of 0 degrees. That's the line voltage. This is the load. All right. I'm going to say this has a real power of 110 kW. I'm going to say that it's got a power factor of 0.85 lagging. Right. Now, I want to reduce that, or I want to increase that power factor to 0.95. I want to go from here to here. This is 1, this is 2. That's what it was. I want to get it to 0.95. That's my goal. I'd like to get it to 1, but for now we're going to go to 0.95. You all see what I'm doing? So here's the steps you do to solve this problem. First thing you do, yes sir?
What does it say inside the
Load. So, all right, now what I'm gonna do is first draw the power triangle associated with this as is. So it looks like this. This is gonna be, call it 1. I have a real power, that never changes, of 110 kW. Now, I know the angle here would be what? Inverse cosine of 0.85. So my angle was cosine minus 1 of 0.85. I want to say it's 29, it's 26 degrees or 29, I don't know. What is it?
31.78.
31.5?
78.
31.78 degrees. So inside here, I know the angle already. 31 point, did you say 875? 785, sorry.
Just,
All right,
just-
now
just-
I can get this value JQ. Can I have that, class? How do I get it? Opposite over adjacent is tangent of that, right? Correct, class? So I can say this JQ is equal to J times this, 110 times 10 to the third, right? Times the tangent of 31.785 degrees. And give that to me. What is JQ? What is Q? Just take the tangent of 31.785 and multiply it by 110 times 10 to the third. Anybody?
68.17.
So it's J 68.17, and that would be K var. Right? Got me? Just keep watching, you're gonna see how this is done. That's the first, that's what I started with, right? Where do I wanna go? Well, the resulting thing that I wanna get is this power triangle. That's one. I want this one. I want to have same real power. You can never change that. The real power is still 110 kW. But now, this angle changes. I started with 0.85 inverse cosine. Now I have to take the inverse cosine of 0.95. So this angle was 31.785 degrees. Where does this angle go? Cosine minus 1 of 0.95 is, anybody?
18.19.
Say again?
18.19.
18.19 degrees. Therefore, what is this JQ? Well, it would be tangent of 18.19 times 110. Can anybody give that to me, please?
36.15.
So it's J 36.15 kVR. Everybody follow me? That's where I want to go. Everybody got that? I was at 0.85, I want to go to 0.95, correct, class? Follow me on this? Ideally, you would want that power factor to be 1, or the aim, you don't want any reactive power. But we're getting it closer, so this is where we're going. It's reduced by a total of what? What is the delta Q? That's equal to this, 68.17 times 10 to the third, right, minus 36.15 times 10 to the third, or where do we get the delta Q? What's the change in the reactive power? People? What, 31, 32 about?
Yeah.
What is it exactly?
32.02.
Thank you. All right. Now, where does that come? How are we going to reduce it? We're going to add a capacitor that has negative 32.02 K var associated with it. Is everybody following? The one thing I didn't give you is the frequency. Almost inevitably, everything works at the line frequency of the power company. Our frequency is 60 hertz. So that means omega is 2 pi times 60, or it's 120 pi, or it's about 377 radians per second. Now write that, you're going to see this number over and over again. If the frequency is 60 hertz, omega is about 377, or 2 pi times that. How many of you know that frequency and omega, right? Almost all engineering, as far as I know, uses this commonly. And that's a 60 hertz line there. All right, now, how do we get the value of the capacitor we need? We do this. We know that Q of the reactive power of the capacitor would be the minus J omega C times V RMS squared, right? I know that's going to be equal to, it's minus JQ of the capacitor. Therefore, we can say the total amount, this is like the Q of the capacitor. So we can say the Q of the capacitor is equal to omega C times V squared, that's VRMS squared, and we're after C, so C is equal to Q of the capacitor divided by omega divided by V squared. Now for our problem, the delta Q that we had was 32.02 times 10 to the third. Omega was 377, or 125 if you want. Now the voltage is 480. And you square that and you're going to get a single value there. Can you give me that value?
Is that Q cap equals omega CV squared? Okay, sure.
It's just the capacitor's complex power. I got rid of the J's because sometimes they're just distracting. That's the Q, is it's reactive power. Do y'all follow me on this? How many do? All right? Right? We're just calculating reactive power on the capacitor to get the size of the capacitor. We're given the reactive power actually. We got it from going from that power triangle to this power triangle reduction. Correct, class? So what is this value going to be for C? The 480 is squared, remember. 3.69 times 10 to the what? All right, and the units of capacitance are farad. I want to tell you it's a fairly large capacitor. Yes, sir.
What is this in that thing with the Q?
This?
No, and then
This?
no, I need to know that that's related to Q.
Further over here?
Yeah,
What does that say?
yeah.
Q on the capacitor. Q associated with the capacitor, CAQ. Okay? That's it. That's what happens when you want to reduce the actual complex power in a system. And that's what industries do. If West Point Petrol would do it, General Electric would do it, any large consumer of power would do this. They basically have banks of capacitors, large amounts of capacitors, that they either attach in they start putting more and more in parallel to get the correct power factor. Now the power company will fine them if their power factor is above a certain amount. And that's why they do it. But it's everybody benefits. I gotta tell you one last thing about these capacitors. These things have to be at the line voltage of 480. They have to have a breakdown strength of at least that. Typically about 10 times that, because you get transients. That's an expensive capacitor. That's a very large, expensive capacitor. Yes? What? What? Well, in Irwin's book, in chapter 5, in the book by Roppel and Gross, I think it's chapter 4. All right? But I pay attention here. Don't worry about the chapters. All right, now what I'm going to do, we're going to take a quiz. Come on down, guys.